Dr. John Hartwig is the Henry Rapoport Professor at the University of California, Berkeley. His research focuses on the discovery, development, and mechanistic analysis of new reactions catalyzed by transition metal complexes. He is well known for contributions to widely practiced cross-coupling chemistry that form aryl and allyl amines, ethers, sulfides, and carbonyl compounds for hydroaminations of alkenes. The discovery of practical CH bond functionalization reactions of small molecules and of polyolefins. He is one of the pioneers to the very well-known Buchwald-Hartwig amination reactions. Recently, he has created artificial enzymes that bring laboratory chemistry inside a protein and inside whole cells. He has created processes for the upcycling and deconstruction of polyolefins. He has received numerous awards. I probably cannot list all, so just to name a few. The A.C. Cope Award, the ACS Award in Organometallic Chemistry, the H.C. Brown Award for Synthetic Methods, and the Wolf Prize, among so many recognitions he has received. He was elected to the National Academy of Sciences in 2012 and the American Academy of Arts and Sciences in 2015. He is the author of the textbook, Organotransition Metal Chemistry from Bonding to Catalysis. Last but not the least, Dr. Hartwig is also an executive editor to the ACS flagship journal, the Journal of the American Chemical Society. With this brief introduction, I now invite Professor Hartwig to join us on the stage. Over to you, Professor.
Okay, well, thank you very much for the introduction, Diksha. Thank you for the invitation. It's really an honor to be invited to give this lecture and to see people coming from all over the world together to join in our shared interests in science. So let me share my screen. Okay, I gave quite a vague title, I think, and abstract to try to decide at the up to the last minute what to talk about. So I'll give a brief introduction to just a broad strokes on what our program has been about over the years, and then transition to how we began to think about the chemistry on polyolefins and ultimately the deconstruction of polyolefins. So in the 35 minutes or so I have here today, I want to focus on that very recent project on the deconstruction of polyolefins. Get my pointer going. Yeah, I think one way to think about our work overall has been to seek to use transition metal catalyzed chemistry to conduct reactions, to catalyze reactions on more and more complex molecules that would be useful for material science, for pharmaceuticals, for agrochemicals, and what I'll talk about today for polyolefins, but complexity in a different way. So this kind of cartoon I often use shows, at least attempts to show a complex molecule with a variety of functional groups on it, some of them being the same functional group but at different positions, and showing that a catalyst can transform one of these functional groups into another functional group with very good site selectivity for one over the other, and also often stereoselectivity and regioselectivity. But we're also very interested in a more classic type of regioselectivity, and that is the selectivity for one CH bond over the other. But when you think about this transformation, CH bonds are usually the unreactive portion of a molecule. And so our group, and of course many others around the world, have been showing that in fact this chemistry can occur at a CH bond over these functional groups where we've learned in introductory organic chemistry reactions usually occur. But while we're interested in developing these kinds of transformations, really at my heart is the understanding of reaction mechanisms and the organometallic chemistry that's behind these processes, making reaction intermediates. Here's an aryl halide complex of palladium with a very large ligand on it as an example. looking at the barriers for individual steps within the catalytic cycle and determining whether they're reversible or not, and what are the energies that are controlling selectivity, and trying to get at that in part by computational methods these days to get a picture of what the transition states look like and what the energies of those are. So today's talk has a little bit less of this mechanism in it, as you'll see why, but we are actively looking at some of the questions about the mechanisms of reactions on polyolefins. That will be papers that we're writing up now as one of my students is finishing his thesis. So just to quickly summarize a series of those functional group transformations, as Diksha mentioned in the introduction, we've worked for many years on the coupling of aryl halides with amines to make arylamines, right? And this goes back to the very early days. We just had a birthday celebration at the ACS meeting, making me, fondly think back on those very early days of the group, where some of the students in my lab, Janice and Fred, and then Anil Gurram and Steve Buchwald's group first published on the cross-coupling of amines with aryl halides. But, we in Steve's group and many other groups around the country continue to work, very actively in this area. And recently we've shown coupling of ammonia and hydrazine and, very high turnover numbers in a very practical way with inexpensive bases and so forth. We've also worked on the coupling of enolates, where the CH bond has a similar acidity to that of the NH bond, and controlling stereoselectivity and the mechanism of the stereoselectivity, and the diastereomeric intermediates in these kinds of processes. But also reactions that would form carbon-nitrogen bonds at a saturated sp3 hybridized carbon, and ultimately looking at iridium for this allylic substitution to give branch products with very, very broad scope. And in work that we very recently published, we could make the carbon-carbon bond joining two different units to make vicinal difluorides, where the conformation about that carbon-carbon bond is controlled by these fluorines, and that affects protein binding of these kinds of products. And finally, for this slide, these sorts of substitutions to make carbon-nitrogen bonds has led us to think about other ways to do that, and led us many years ago into studying the additions of NH bonds to alkenes, and over the years developing systems that can even lead to the addition of an NH bond across an internal alkene with control of the configuration at that site, and chain walking hydroaminations and so forth in recent years. But our story on polyolefins really builds from a parallel effort on installing functional groups more than changing one functional group to the other. And so very early on, we observed that compounds with metal boron bonds had a very high propensity to cleave CH bonds and to deliver this ligand from the metal to the position of the CH bond to generate aryl boronate esters stoichiometrically, then alkyl boronate esters. And for today's talk, it's important to realize that this occurs selectively at the primary over secondary CH bond. With Guiyan Chen turning that into a catalytic process with the CP star rhodium fragment. And then with Tatsuo Ishiyama, a visiting scientist in my group, we collaborated for a series of papers and over a number of years on developing nitrogen-based iridium catalysts with nitrogen-based ligands that would catalyze the borylation of aromatic and heteroaromatic CH bonds to make aryl boronate esters in very practical ways, where the aryne's a limiting reagent. And again, the origin of the synthetic utility of this process is really about the regioselectivity. And so just as one example, if you have an aryne that's kind of electron poor, so not so great for electrophilic substitution, but has orthopara directors, the least reactive bond is where this occurs. That's the most sterically accessible. And the reaction doesn't occur at the halogens. It doesn't reduce esters, right? It tolerates a wide variety of functional groups and still occurs at the CH bond. And finally, in work that is most recently published and things that we're writing up to this day, we've been looking at a family of ligands that's nitrogen-based, but with a substituent next to nitrogen. And so when that group is a methyl group or an anilino substituent, these reactions now occur under mild conditions. They occur at secondary CH bonds, but also at primary CH bonds. Primary CH bonds are pretty, sensitive and and functionalized molecules. And so this was a big step forward for us with Raphael Oettcher's work on discovering that this family of catalysts works. But in the work that was published most recently, we actually showed that that methyl group becomes a diboryl methyl group, and the aniline group becomes a boryl aminophenyl substituent. And it's really this very large substituent with borons on it that's enabling this chemistry to occur. And so the mechanistic origins of the effect of those substituents is something that we're really actively looking at right now. Okay, so I'm going to switch my introduction to something that might seem totally irrelevant, but I'm going to tie it together in a second, right? So we make polyolefins in massive amounts, right? Roughly 300 million tons per year of polyethylene, polypropylene, and a little bit of other polyolefins, particularly polystyrene. And you can see from this pie chart, at least about packaging, a majority of the plastics are polyethylene and polypropylene. And the reason we do this is because they have very high thermal stability and chemical durability, right? So they're pretty insoluble. They don't tear. This plastic bag holds your things very well. You can make cups and so forth out of things, and it has very favorable mechanical properties, et cetera. But there are issues. And so for many, many years, people have been trying to develop systems that would install or incorporate, let's say, polar groups into polyethylenes and polypropylenes, because the plastics themselves, without those functional groups, have limited surface and bulk properties. So you can't paint them very well, and the paint just comes right off. They don't adhere to things. They'll have certain ductility, but that's a little bit limited in how much you can manage that with alkyl substituents. But also, they're difficult to degrade, right? I mean, they're just carbon-hydrogen bonds and carbon-carbon bonds. So it's, they don't biodegrade, and they don't even mix, right? They don't mix with polar materials like a polyester. But even polyethylene and polypropylene, they phase separate. And so it's difficult to make blends of those two if you had a waste stream of those for recycling. So that's why recycled materials really have lower value than the original, in addition to, chain cleavage and other effects of the mechanical recycling. Okay, so that's a general problem we have today. And so we have been working for now quite some time on understanding how to conduct reactions on polyolefins, and that transformed into this issue about how we can manage waste plastic. And so we can think about this as two avenues. If we can install some functional groups into that polyolefin, then we could create new properties from them. Maybe we could grow grafts or just have the properties themselves changed or have substituents off of what we install. And we've been working in collaboration with Brett Helms, who's been the PI on a program at Lawrence Berkeley National Lab on catalytic upcycling of polyolefins that has, I think, been a very productive program. The other is to use those sites to cleave those polyolefins to smaller units and something that would be akin to a chemical recycling process. And that's been supported by an LBNL catalysis program. Again, I think a very successful program there. And so why are we working on this? Well, after all, these polyolefins are just carbon-carbon and carbon-hydrogen bonds. So this scheme here, this first step at least, is a CH bond functionalization, right? And so we got into this whole area because we were working on CH bond functionalization of alkyl CH bonds, and that would be potentially applicable to the polyolefins. But there are real challenges there. Right? And so in contrast to, trying to do CH activation on a carbohydrate or some complex, natural product or medicinally active compound that has a variety of functional groups, the problem here, right, is that the materials, they require high temperature to melt or to dissolve in some solution. And so the catalyst that has to functionalize the strong CH bond in this very long and tangled chain, and has to be stable at high temperature, and has to operate in a solvent that would be able to dissolve the material and then not react, right? Because we want to functionalize the polyolefin with this strong bond instead of the solvent. And many of the ways you think about doing this might be radical chemistry. And part of the issue with radical chemistry is that that can lead to cleavage. So you may functionalize it, but that can lead to cleavage. Or, as I outlined in the previous slide, you could maybe use that functional group to controllably cleave the olefin. So this chain scission of the CC through CC bond cleavage can be a detriment and a sort of a side reaction, or could be harnessed to create materials that would have shorter chains and could be useful for other purposes. But whatever we do, right, we hope that by installing these functional groups, we're going to enhance the properties. But we need to keep in mind that if we put in something small like a hydroxyl group or an oxyl group, make a ketone there, those are small groups and really may not influence the crystallinity that much. But if we put in larger groups like an amino group, that can disrupt the crystallinity of the material. And that may be to our benefit or the detriment, but we just need to keep in mind that all functional groups that you install are not going to have the same effect on physical properties. So how we got into that area then relates to that introduction I gave you on CH bond functionalization and developing, catalytic transformations. And so what we've shown over the years is that with the very original rhodium catalyst we had for the borylation of CH bonds, we could functionalize things like the primary CH bonds of polypropylene. Polypropylene has, methylene CH bonds, maybe not shown so well in this graphic, but has the methylene CH bonds and has a methine CH bond that's the weakest CH bond. And of course, the least reactive, the strongest CH bond is the methyl CH bond. But this borylation chemistry we developed will install boryl groups at the primary CH bonds of polypropylene and other copolymers. But what we wondered recently was whether we could actually functionalize the primary CH bond at the chain end of polyethylene. And I didn't really think that was possible because there are so many methylene CH bonds and such a low concentration of methyl CH bonds in a polyolefin. But what Molly McFadden has recently shown is that we can actually do that reaction. We can use the diboron compound with our most recent iridium catalyst that is very selective for primary CH bond, is more active than the rhodium catalyst that we studied initially, right? And be able to functionalize now the ends of a polyethylene chain. Now, it's not perfect, right? It's about 30% yield relative to those methyl groups. And so if we have high density polyethylene shown on the right, we have, maybe a little more than 2 because there's a little bit of branching in HDPE. But for the most part, right, we have methylenes and the chain end, and we can get about 30% of those chains functionalized with the boryl group at the end and then change the property of those chains. But as the degree of branching increases, so we have low density polyethylene, we can actually put in what is an average of 2 borons per chain, which then would allow us not just to change the properties, but maybe to link those materials through those chain ends. So there's a lot of ongoing work here on being able to then use these carbon-boron bonds to do, say, a Suzuki cross-coupling at the chain end, or oxidation or amination to put in polar groups or non-polar groups of varying sizes, and have that group specifically at the chain end rather than the mid-chain, whether it's from a comonomer that was incorporated or some CH activation in the middle, right? And look at the effect of having the group at the end versus the middle and how that changes properties. And it's going to change the influence of that functional group on crystallinity to different extents because of where that group is. So I don't have time to go through in detail all these other different transformations, but I just want to point out in brief that the original borylation, where we would oxidize that, led us to, of course, think about direct oxidation. And because this chemistry was selective for primary CH bonds, we wanted some chemistry that would go after the secondary CH bonds of polyethylene because there's so many of them. And we Alo Bonescu and Sunwoo Lee really leading the charge in our group to oxidize these to lead to a material that would have different surface properties. So you could paint it and it would adhere to metals. And then Nico Chichia in the group developed a copper catalyzed amination of polyolefins that would lead to changes in bulk properties, changing the ductility of that material and allowing it to be stretched 1,000 times its length, so 100 times, 10 times its length in these tensile tests, but also to adhere to metals like aluminum and stainless steel, et cetera. So those functionalizations would lead to a change in properties. But what I want to spend the rest of my time talking about is the deconstruction of polyolefins by installing a functional group into the materials in a kind of an unexpected way, and then using that again as sort of a starting point for deconstruction. And so while we've developed these oxidations and aminations and borylations and are continuing to work on those and some new aspects of that, I want to spend the rest of the time on this kind of scheme over here on the right about deconstruction. And naturally, we're not the only people to be thinking about deconstructing polyolefins. There's actually been a lot of support over the last 5 years or so, or maybe a little longer, on polyolefin upcycling to address the plastics waste issues. And so one approach is just pyrolysis, and that will break chains. It also makes arenes, right, by cyclization and dehydrogenation chemistry. And so you get a mixture of alkanes, alkenes, and arenes, and actually methane as well. And some of that methane gets burned and can get burned to be used in this pyrolysis. But in any case, that's one approach. More controlled approaches would be to do a hydrogenolysis, where you would cleave the chains. That will generate shorter chains, but they are alkanes. And this very depending on the catalyst and so forth, there's varying degrees of formation of methane in this as well by that terminal CC bond cleavage. But there are some catalysts that work very well for this, but ultimately you get a mixture of alkanes. The same is true for alkane metathesis. This is kind of a slick way to do this where you don't use hydrogen, you use a shorter alkane plus a long alkane, and with a multiple catalyst can lead to varying chain lengths, again, of alkanes in this process. And finally, there's ways to generate arenes where there would be dehydrogenation, cyclization with platinum or even without platinum to generate these kinds of cyclized materials, much like you see up here. In this case, you get typically di-substituted arenes, ortho-di-substituted due to the mechanism of the cyclization here. But what we wanted to do was to come up with a method that would actually produce a single product, because these are all generating mixtures. And so would it be possible to take these polyolefins and make a single product that would be in high demand? And so that's what we had some brainstorming on at group meetings when some of these funding opportunities came out. And ultimately, the first scheme was to use a series of catalysts to be able to break this down to make propene. And this was really Stephen Hanna's idea, a graduate student in the group, to capitalize on a little bit of the work that's been published and think about applying that to polyolefins. So the scheme was the following. You'd have polyethylene and you do a dehydrogenation of that. So that was known, as I'll show you in the next slide, that you could do that. And then maybe if you had that alkene, you could do an olefin metathesis on that to generate alpha olefins now that would have long chains. Maybe not straightforward to do olefin metathesis on a polymer that's entangled and requires high temperatures for melting, but we considered that you could do that. And if you did do that, then if you isomerized with another catalyst that alkene into the chain by one position, now metathesis at that carbon-carbon bond, double bond, is going to make propene, and then you end up with a chain that's one carbon shorter than you started with. And if it isomerizes and metathesis again, you get ethylene, propene out, and then a chain that's one carbon shorter. And if you do that 1,000 or 2,000 times, depending on how long your chain is, you can take this all the way down to propene. So that was the idea, and there was some precedent. Lars Gussen, over 10 years ago, had shown that you could take allylbenzene, move the double bond in, do metathesis, and make styrene from that with these two catalysts, this for isomerization, palladium dimer for isomerization, ruthenium, of course, Haveda Grubbs catalyst for the metathesis. And we weren't the only ones to think about this scheme. Susanna Scott and Gironet's group had, in a collaboration, together with people at Dow, had come up with this scheme. Here's their table of contents entry, I think from JACS. And And Tuba in Hungary had been working on a catalyst for this, and he's a very, very active catalyst for the metathesis step on this, and to take long chain alkenes like hexadecene, and be able to take that with ethylene and go to propylene with very high turnover numbers. Right, but we wanted to do this on polyolefins, and we were working in parallel with those groups, and so we all published about a very similar time. So um, these are all about making propene. And so why do you want to make propene, right? Let me put this in the scale in the context of how much polyethylene we make, how much gets recycled. That's kind of depressing that it's so small, right? But even if we increase that by, say, 25 times and made propene, the reason I compare those is because there's a propylene gap, as they say, right? So this red line is the propene that is kind of desired, right? The demand for propene, mostly for polypropylene. And then here's how it gets made from refining, right? And so there's actually a 35 million metric ton gap here, right? And so if we took all of the polyethylene that we collected from recycling and turned it into propene, we'd only begin to fill that propene gap. So there's a demand for propene that would be, a valuable output from a deconstruction of polyolefins. Okay, so will this scheme work, right? And so what we knew from Coates and Goldman paper from quite a while ago, with lower molecular weight polymer and an iridium pincer catalyst, right? So we tuned up that catalyst, so we had something that was a pre-catalyst that was convenient to work with base generating in the iridium 1, and then to legitimate polyolefins, this high density polyethylene at high temperatures, right? With T-butyl ethylene as a hydrogen acceptor. So it's a transfer hydrogenation, taking hydrogens out of this polymer, putting them into T-butyl ethylene, making these dehydrogenated materials. And how can we tell if we made them? Well, we can just use NMR spectroscopy, right? There's our olefinic resonances shown here. And, we can't install a huge amount of alkene, but you see we don't want to. We can get up to about 3.5%, and that can be dialed in with the amount of TBE that we add, T-butyl ethylene we add. Okay, so can we degrade that? Will the olefin metathesis step work on this unsaturated polyolefin where there's only a small amount of olefin in there? And so we ran that reaction, and then we tested whether we did cleave the chains by using GPC, gel permeation chromatography, to measure molecular weights. And so the black line is the starting material. The red line is dehydrogenated material from the catalyst I just showed you. The blue line is actually with platinum zinc catalyst that comes from Alex Bell's group, my colleague, who we've been working with, and you'll see that in a minute. But that gives a little bit difference in molecular weight, but not too different. But then you take that material and you do the ethanolysis, the metathesis with ethylene, and you can see you dramatically reduce the polymer molecular weight down by about a factor of 20, consistent with metathesis occurring on the dehydrogenated material. So then the question is whether we can put these catalysts together and get that unsaturated polyolefin to convert all the way to propene as was designed. And so what this graph shows on the y-axis is the yield of propene, and on the x-axis is the amount of olefin we put into this starting material, right? I said we could do that in a controlled way with the amount of T-butyl ethylene to low amounts below, 0.25% or so, all the way up to that 3.5%. And what you can see is that if we get the right amount of alkene olefin units in the starting polyolefin, we can get a yield that approaches 90% of propene. And just to explain that yield, it's not per chain, right? It's per carbon, right? Per monomer unit. All of that material goes in close to 90% yield to propene here. So if we don't have enough olefin, I guess the catalyst needs to run too far along the chain to get it all the way down to propene. And if we put in too much olefin, that's a detriment. And I don't have all the mechanistic slides on this, but we showed that if you make dienes, that poisons the catalyst. So that becomes a problem. And for low density polyethylene, I showed you earlier, that has more chains in it, or more branches in the chain. And it's a little bit harder for the metathesis probably to make its way through those branches because that forms more substituted alkenes. And so we think that's the origin of this effect, but still you get up to about 70% yield. Now, of course, we don't want to just take, as they say, virgin polyolefins, right? Make the polyolefin, then just deconstruct it. You really want to do this on waste material. And what we show here is that a milk jug or a solvent bottle made with high density polyethylene, we can take that in quite good yields all the way to propene. Even a shampoo bottle, a carrot bag, and even this, beer bottle, a beer can top that's got a lot of carbon black in it and this dark color, it'll still, not in this high yield, but still in substantial yields, go all the way to propene. But if you think about what we've done, right, we've developed a system that's got iridium, ruthenium, palladium, three precious metals together to make a very inexpensive material. Now, that could be okay if our turnover numbers are very high, but these are homogeneous catalysts. So, they're not going to be recyclable. And so ultimately, this is, some of the world's most expensive propene that we're making from this process. So, we wondered whether we could replace these homogeneous catalysts with heterogeneous catalysts, preferably from earth-abundant metals, to make this work. And if you think about the steps, the dehydrogenation, the metathesis, and isomerization, they are all reactions that are known reactions with heterogeneous catalysts. And so to do this, we teamed up with Alex Bell, my colleague in engineering and chemical engineering, and Natalie Lefton is a postdoc, and Jisoo now up at Lawrence Berkeley National Lab, who's very good at reactor design and forming heterogeneous catalysts, and Jiang, his postdoc. And so RJ Conk, whose picture you saw in an earlier slide, has been working together with Jules Stoller, an undergrad, on this chemistry in my own lab. And so this is the idea. The idea is that we would use the tungsten oxide on silica for olefin metathesis. That's a commercial catalyst for doing olefin metathesis in various processes, and sodium on alumina, a commercial catalyst for doing olefin isomerization. And we put those catalysts together. Instead of ruthenium and palladium homogeneous catalysts, we do the reaction on hexadecene with ethylene, and we get propene out. And we get propene out, not perfect yield, but quite good yield. And if we take a model of polypropylene, I didn't show you any chemistry with polypropylene with the homogeneous catalyst because it doesn't really touch it, right? It won't do the deconstruction of polypropylene. But these two catalysts, it looks like it might. So we take this model compound we made of desaturated polypropylene with ethylene, and we get a mixture of propene and isobutylene. Propene from the methylene units, isobutylene coming from this CH methyl unit plus ethylene to make 4 carbons in the isobutylene. Do we want to make isobutylene? Well, yeah. Isobutylene, right, comes from isomerization of butene and, at high temperatures, skeletal isomerization. And it's hard to separate because the boiling points are almost the same as they are for N-butene. So my understanding is that industrially, this is actually hydrated to make an alcohol that you separate and then dehydrate to get back to the isobutylene. And, it's used a lot. It's used to make polyisobutylene. It's kind of a soft plastic, even used in cosmetics, I think. But you can combine it with isoprene and, that make tires out of it. And you can also make very high octane additives for fuels by doing addition of CH bonds to make this octane here. So making isobutylene would actually be a valuable product to form here, or isobutylene would be a valuable product. So let me go back to this slide then. Okay, we can make those two materials, but the disappointing part then is if we take that on polypropylene, which seemed to work fine, as shown in the second equation, in small molecule form, but we take the polyolefin that's saturated with our platinum tin catalyst to dehydrogenate, tungsten oxide for metathesis, sodium for isomerization, and we get the products, but we get that in much lower yield than we got with the small molecule, low turnovers. But what actually happens, in part at least, is that these materials get rehydrogenated with the platinum to generate light alkanes as well as these alkenes. So how can we stop that? right? How do we avoid the re-reduction? Well, maybe one thing to do is just simply leave out the platinum and the tin, right? And so take the, the polyolefin itself with tungsten and sodium and give that a shot without the rehydrogenation. And it turns out that works great, right? You take polypropylene with ethylene, you get, about 90% yield of the mixture of these two alkenes. And if you do that on polyethylene, you get a close to 90% yield of propene with reasonable turnover numbers, at least for the start here, with these two catalysts that are now heterogeneous and from earth-abundant metals. But we have kind of a mechanistic problem here because the whole scheme is based off of this olefins, isomerizing and doing metathesis. But our starting polyolefin, doesn't really have any olefin in it. It might have a tiny amount of, but, just that's in there, but not in the start, but not enough. So what's happening there? Okay, we're actually cracking the material. So we're running this chemistry at 320, right? Low temperature for heterogeneous catalysis, of course, high for homogeneous catalysis, but not too bad. But sort of special property of entangled polyolefins is that at those temperatures with mechanically stirring, you do get chain cleavage. Okay, but if we have sodium on alumina in there, that will install olefins along the chain by catalytic scission and some sort of dehydrogenation that's happening. And it also, of course, isomerizes that to the internal position. So how do we know? Right? Again, we can just take proton NMR spectra of that and measure the amount of olefin that's in there versus methylene. And we see that we get a little bit from just the thermal cracking. But with the sodium on alumina, we generate more of it. And with tungsten oxide on silica, we get a little bit more, but not nearly as much as with the sodium on alumina. We know we crack the chains by GPC. Again, you can see molecular weights going down. It goes down a little bit more with the sodium on alumina catalyst in there, but not as dramatic as just the thermal process. But nevertheless, it's enhancing the amount of alkene that we generate. And then if we look at polypropylene, the tungsten will lead to enhance the chain cleavage in this case. And we think that's because it's an acidic catalyst and now we've got more substituted carbons. And the other thing that it does is promote skeletal isomerization. So now we dehydrogenate, or crack and dehydrogenate. But really the second element that's important in a minute is that polypropylene has too many chains, too many branches thermodynamically. And so at these temperatures where skeletal isomerization can happen from sort of acidic catalysis, we actually straighten the chain to put more methylene units versus methine or CH-methyl units in it. Okay. So how do we know that's going on? Again, by NMR, we can see the tungsten oxide on silica enhances the amount of olefin that gets put in there. And it also reduces molecular weight. Okay. And so here's the starting material, and here it is cracked with no additive, and then cracked is a mistake down. It should be tungsten oxide on silica, giving about the same degree of cracking, but enhancing the amount of olefin, as you see here. So now we're set up because we're cleaving the chains in a simple way. We're not doing catalytic dehydrogenation with a homogeneous catalyst and all that. We're just cracking the chains, and that process puts olefins in there. And so now we can just take HDPE with the two catalysts and we get 90% yield of propene now. Low density, same, a little over 90. Linear low density, copolymers with alpha olefins, same 90% yield of propene. And importantly, of course, we can do this with waste. So we take that same bottle kind of we showed before. Now it works great, 90% yield. Take a sandwich bag. It's a little bit lower yield. I'm not sure what the error bars on these, but still high yield for taking a bread bag. And a mixture of polyethylene and polypropylene in high yield makes propene and isobutylene, the shaded bar here being isobutylene. And that, of course, suggests that the polypropylene will also undergo this process. And indeed, if you take isotactic polypropylene, you get a very high conversion. You get more propene than isobutylene, and that's because of the chain straightening I showed you in the previous slide. There's no more methylene units than methine units after the initial cleavage and the isomerization that's happening. skeletal isomerization that's happening, right? And so, yeah, you could get an unequal ratio of those two materials. And really, we're taking polypropylene back to propylene, right? So that really is a circularity that's happening by generating that material. Atactic works fine, and then sort of waste centrifuge bottle, plastic centrifuge bottle also works fine. So, is the sodium on alumina we're generating is actually from sodium metal and depositing that on alumina and making a basic alumina. It's not really the way you'd want to do it industrially. And are there other metals that will work? And so what we show here is that for this process, you can just use, sodium carbonate instead. You can use magnesium, potassium carbonate works fine. Lithium is not as good, but potassium and potassium hydroxide. So other alkali metals and alkaline earth metals will also work. And the amount that you put on does affect the yield. And so, there's going to be an optimal amount to be able to generate high yields here for the amount of potassium per the surface area. Now, of course, important metrics are going to be recyclability. And so here we show the results in black bars for running one after the other, 3 rounds. And we lose about 50% of the catalyst activity for each of those rounds. But we have 2 catalysts in there. And so if we're losing the catalyst activity, is it due to the tungsten or due to the sodium? And it turns out it's due to the sodium, because if we replace the sodium catalyst after each round, we maintain activity. And so we really need to focus on how to regenerate that sodium catalyst from one round to the other, not just replace it, but regenerate it. And we have schemes that I think are working quite well, although I don't have time and not enough data to show that here. Now, what about additives, right? And so if we add 5%, quite a lot, right, of PVC or PET, polyethylene terephthalate, or plasticizers in, we do inhibit catalyst activity. And so that's something we really need to address. But we're hopeful that that can be addressed, because if we just use sodium carbonate instead of sodium on alumina, we actually have a higher tolerance for PVC than we have with that with the catalyst that is made just from sodium on alumina, shown right here. So yeah, so anyway, we're working on that. I don't, that's going to be an issue, but there are, approaches, particularly just taking advantage of density to separate things like PVC from these polyolefins. And so it's not perfect separation, but maybe we can build a system that has enough of a tolerance toward those impurities that it becomes practical in the end. So finally, I'll close by showing just some work on scale up, right? So if we think about making this a semi-batch, right? So in the experiments I showed you, they're just batch reactions. Put stuff into a par bomb, add the ethylene, run the reaction, and measure the head gas that comes out. Here we're flowing the ethylene through at varying pressures. And what we find is that the reaction works with just 1 atmosphere of ethylene to make propene, but not in as high a yield. But if we just increase the pressure, we can get back up to our 80% yield or so. So we'd have to recycle that ethylene to get back, probably, to make this practical. But in any case, we can get high yields in this kind of a setup. And I just show this picture and the people involved. So Jules is an undergraduate in chemical engineering who's been working on this chemistry with RJ. And Jake is just graduated from my lab, but he was a chemical engineer as an undergrad, so helped set this up. This looks a little bit different than vials and round bottom flasks that we're used to working with. So this has really been enabled by this collaboration with Alex. So the final thing I want to show is that if you run this in a different reactor setup, more of a continuous reactor, we run the reaction actually to partial conversion. And so we don't get all the way to propene. But what you can see is that we actually get some butenes and we get some longer chains out. And so we can collect the volatiles. This is very low down in dry ice temperatures to collect or below. So we can make a big quantity of the material. And this is the composition of that material. But the part that didn't condense, that condensed at higher temperatures, are these longer chains. And these are all alkenes. And what we find is that you actually make pentenes, hexenes, heptene, octene. And so these are all kind of in proportion to the volatility of those materials. And so instead of making propene, we can make these materials. All right, so what does that say about mechanism, right? So in the scenario I showed you, we've got metathesis and isomerization. So we've got the unsaturated material. We do a metathesis to make alpha olefin. Of course, the metathesis on the alpha olefin is degenerate, right? So that doesn't do anything. But if we isomerize one in and do metathesis, we make propene. But we make propene in a long chain. And so in this scenario, we always are making propene and leaving long chains. Right? And so that's what happens when metathesis is faster than isomerization. But if isomerization is faster than metathesis, then when we make the alpha olefin, and then when the isomerization occurs, that goes further into the chain, and then metathesis occurs, and you get longer chains. And so I think this is what's really happening in there. It's not just one carbon at a time, but it's chunk by chunk, and then eventually that'll all go down, right, to make the alpha olefin, to make propene. But earlier on, we make alkenes that could be turned into alpha olefins of longer chain lengths. And so by controlling the relative rates of these two by catalyst identity, catalyst fraction that's in there, we hope that we'll be able to control this, right? And be able to modify the ratios to form those products. So I'm going to end there and just say that, this is our approach then to use some of our experience in CH activation to functionalize and deconstruct polyolefins. And I want to stress that, we've worked on this for quite a while. So some, visitors came in early on to start this chemistry, but this has been going for quite a while with very talented people, particularly RJ and Stephen and Jules in the most recent work. And a lot of this is in collaboration with BASF as part of the California Research Alliance. Again, I mentioned the collaboration with Brett, collaboration with Alex and G that's really been essential. And I do want to point out that this has been funded by the Department of Energy, Basic Energy Sciences, both in the material science side and the catalysis side. And so great appreciation to them, particularly in these days when our federal funding is getting challenged. And thanks for your attention.